Hi everyone, welcome to this video on deriving the Taylor series formula. So the Taylor series formula, this pretty much says that any function, right, if we have just some function f of x, this can be modeled as an infinite series going from 0 to infinity of just some infinitely long polynomial. And this polynomial can be expressed as some arbitrary term a sub n times x minus c to the n, where c is just the center point of the Taylor series. Remember, a polynomial can be centered at any point. So for example, if we had like a function f, which is like f of x equals x minus 4 squared plus 5, we know that this is a quadratic and it's centered at x equals 4. And it works exactly like that in a Taylor series. This c is just where it's centered at. So let's go ahead and try to figure out what this a sub n actually is and how we can sort of apply it in more of a functional context. So let's go ahead and expand out this series then. So the series f of x equals the sum from 0 to infinity of a sub n times x minus c, all that to the n. This is equal to a sub 0 times x minus c to the 0, that's just 1, plus a sub 1 times x minus c to the first, which is just x minus c, plus a sub 2 times x minus c squared, plus a sub 3 x minus 3 cubed, and this just goes on infinitely forever. All right, so from this we can't exactly get just a general overview of a sub n, but we can get one of the a sub n terms, a sub 0. We can figure out what that is by essentially just killing off all of these terms right here. How can we do that? Well, let's go ahead. If this is true for all x, right? For all x, this can be modeled as a certain function. Then we can go ahead and let x be the center point. And I should clarify what I said, because sometimes there will be cases where this doesn't apply for all x. But for all x near the center point, then this formula will work. So we can go ahead and just let x be the center point. So let's go ahead and write let x equals c. And as a result, we get c minus c, which is 0, plus a sub 2 times 0 again, plus a sub 3 times 0. So as a result, we're just getting a sub 0 plus an infinite sum of zeros. And we all know that's just going to be a sub 0. And so f of c is going to be a sub 0. And this is just the function evaluated at c. So that's pretty much our first term, a sub 0. But we can't get a pattern from that. So let's go ahead and try doing some other step to figure out this general pattern. Well, we know what an a sub 0 is, so let's try to figure out what this a sub 1 is, and maybe we could just go in a chronological order, right? So how can we do that? Well, we got to get rid of this a sub 0, and we got to get rid of this x minus c, and then just pretty much make it so we can ignore all of these a sub 2, a sub 3 by just letting x equal c. There is a way to do that. Let's go ahead and differentiate this infinite sum of polynomials. So f prime of x, right? This is going to be the derivative of a sub 0 is just 0, 0 plus a sub 1 times the derivative of this, which is 1. This is going to be a sub 1 plus a sub 2 times the derivative of this is just by the power rule. It's going to be 2 times a sub 2 x minus c plus, and then repeating the process, 3a sub 3 x minus c squared. This is again by the power rule. And then I'll go ahead and just showcase the pattern going on here by making up the fourth term in this derivative expression. This fourth term is going to be 4 times a sub 4 x minus c cubed, and so on and so forth. And you can just get that because the next term is going to be a sub 4 x minus c to the fourth, and you just do power rule to get this derivative right here. Anyways, let's go ahead and let x equal c again. So f prime of c is going to be a sub 1 plus this infinite string of zeros again, because we're going to have c minus c in every term that isn't a sub 1. So s sub c is just a sub 1. Now let's go ahead and repeat the process because we still don't really have a general pattern going on here. I mean, we could definitely say that it's just going to be like f of c, f prime of c, f double prime of c, but it's not. And I'll show you how. So, let's go ahead and differentiate the function again. F double prime of x is going to be, this is going to be 2a sub 2, derivative of this is 1, plus 3 times 2a sub 3, x minus c, plus 4 times 3, a sub 4, x minus c squared. This is again just by power rule again. You can check it with yourself. You can check it by yourself. And then plus, now I'm going to repeat this pattern going on here. 5 times 4, a sub 5, x minus c cubed, and this goes on forever. And again, we're going to let x equal c. So f double prime of c is equal to 2a sub 2. And notice something here. Unlike this a sub 0 and a sub 1, this a sub 2 has a number in front of it. So in order to accommodate for this, we're going to say that a sub 2 is just f double prime of c divided by 2. All right? And you're going to notice here, that kind of just breaks the pattern that you could see with these first two terms. And again, you might think that there's another pattern that's going to be broken. And you might think that there's going to be another pattern here. It's going to be f prime of c divided by 1, f double prime of c divided by 2, f triple prime of c divided by 3. That's not the pattern. And we're going to prove that. We're going to prove that it's not. So, differentiate again. F triple prime of x. This is the third derivative of x. This is going to be, killing off this constant, this is going to be 3 times 2 times 1 times a sub 3, and you're going to see why I did that, plus 4 times 3 times 2, a sub 4, x minus c, plus 5 times 4 times 3, a sub 5, x minus c squared, plus 6 times 5 times 4, just to add that extra term, a sub 6, x minus c cubed, and this goes on infinitely forever. So, repeat the process. Let's let x equal c. So we're going to get f triple prime of c. This is going to be 3 times 2 times 1, a sub 3. That looks like a minus. There we go. This is 3 times 2 times 1. But what is 3 times 2 times 1? Yes, it is 6, but how can we notate that in a different way? Well, there's a thing called a factorial, and we're going to use that. So 3 times 2 times 1, this cascading descent of numbers that are just being multiplied together all the way to 1. This is the same as 3 factorial, a sub 3. So therefore, a sub 3 is equal to f triple prime at c divided by 3 factorial. And now we can stop differentiating. Because if we were to differentiate one more time, you'd notice that we have a 4, this would be gone, all this would be differentiated, but this in particular, what we're going to be focused on, this is the fourth derivative, x is going to be 4 times 3 times 2 times 1 times a sub 4, and that's 4 factorial times a sub 4. If we found a sub 4 would be the fourth derivative, and this is how we notate derivatives higher than 3, the fourth derivative at c divided by 4 factorial. And that coincides with this pattern right here. So, and we can actually go ahead and recap here. So this a sub 2, right? We said this is f double prime of c divided by 2. But 2 is actually also 2 factorial, because it's just 2 times 1. And then this right here, a sub 1, this is f prime of c divided by 1 factorial. And this is f of c divided by 0 factorial. And 0 factorial is actually 1, because nothing's being multiplied, so we just stick to 1. So, therefore, we have a general term in mind. We can say that a sub n is equal to the nth derivative at the center point divided by n factorial. And as a result, we get that the function f of x is modeled by the infinite series from 0 to infinity of the nth derivative at c divided by n factorial times x minus c to the nth power. And this is the Taylor series formula. And that's it. This Taylor series formula right here, this summation, you figure out what all these nth derivative patterns are, and this pretty much is the universal formula for modeling literally any function. But yeah, that concludes this video on deriving the Taylor series formula. Next, we'll be looking into figuring out how to model actual functions with this Taylor series formula right here, and in the future, figuring out some further topics with this formula. But yeah, that concludes this video, and I hope to see you in future videos.